So this is a short lecture on the material in sections 5.5. Really, I think this is a very important section, something you'll use a lot. I think in the rest, if you take Calc 2, and whereas let's say like something like there are important topics like taking a derivative, via the definition, or finding a Riemann sum, probably something you're not going to see so much in Calc, maybe not ever. But substitution is something we use all the time, and so in this section we'll kind of have some easier examples of it. Can be kind of, some of the problems I think in Calc 2 using substitution can be difficult. So here's kind of a good example. So we know that an antiderivative, if we take the derivative of an antiderivative, we get the original function back, right? So let's say we start with this function here in this example right here. Let me see if I can make this a little bit bigger. Yeah, so this function right here, we're going to take the derivative of the quantity x squared minus 3 raised to the fourth. Now, we can do it with the chain rule. And so what you get there, yeah, so there's, accurate use of the chain rule, and you get 8x after you do the simplification, 8x times the quantity 8 squared minus 3 raised to the third power. Now, suppose I said, okay, now let's but let's say we start with 8x times 8 squared minus 3 raised to the third power. Let's find the antiderivative. Well, you could expand x squared minus 3 to the third power. Easy to make mistakes, plus it's time consuming. But an easier way to do this, well, we're going to learn an easier way to do this. We're going to learn something called substitution. Okay, but basically, yeah, so we know that the derivative of x squared minus 3 raised to the fourth, the derivative is this function right here. So 8x squared minus 3 raised to the third power. So the antiderivative of 8x times x squared minus 3 raised to the third power is x squared minus 3 raised to the fourth. So what we're going to do is learn some kind of methodical way of doing this, so we don't have to expand x squared minus 3 raised to the third power. Because let's say it wasn't to the third power, let's say it's to the fifth, or something, something that would really take us a lot of time to expand. Okay, so here's just a few more. Okay, so like let's take the derivative of sine of x raised to the third power. And so yeah, using the chain rule, we get 3 times sine x squared cosine x. So we know that the antiderivative of 3 times sine of x times cosine of x is sine x cubed. Again, we don't really have a methodical way of doing it. You might be able to recognize that. If you're pretty familiar with the derivatives in the chain rule. So here's another one, which is kind of a common problem. We have the square root in the denominator. Oh, it's not the square root of x. We have a function. We have function composition. Square root of 2x minus 3 in the denominator. And so, yeah, or in this case, yeah. So we take the derivative, and yeah, so what do we get here? We get negative 4 over 2x minus 3 to the 3 halves. And so what is the antiderivative of negative 4 times over 2x minus 3 raised to the 3 halves? Now, if it was just an x in there, instead of 2x minus 3, well, that would be pretty straightforward. Well, now maybe we have to take into account the chain rule. What do we do, with that 2x? So again, we're going to just learn, just so we don't have to guess or kind of go backwards in our head all the time. We're going to just learn some methodical way. And here's just one more. Integral of 2x secant squared of x squared. That looks like kind of a mess. But it turns out the antiderivative is just tangent of x squared. Okay, and so the important thing here is that the chain rule creates a product. So we're going to use that in this product in what we call the substitute, this very practical algorithm or technique for finding antiderivatives, and that is changing the variable. So now we know that. Let's look at this example right here. I know that if that was just the square root of x, well, that would be relatively simple to integrate or find the antiderivative of. We could just write that square root as x to the 1/2, but now it's 4x plus 1. What are we going to do with that for? We know somehow the chain rule is going to be involved in this. So here's just kind of these steps, which I believe come from the book. Okay, so you want to find what's called the inner function, and we just call it u. See, if we can just integrate u instead of the square root of 4x plus 1, it becomes a lot easier. then you find du, and du will be written in terms of dx. So, okay, so we're just going to replace dx with the, we're going to change the variable of integration from x to u. And so here, let's just look at this kind of nice, simple example. Okay, so the inner function, right? So it's function composition. We're taking the square root. In this case, we're taking the square root of u, where u of x is 4x plus 1. Now du is just 4 dx. And so let's just solve for dx, and we get that dx is 1/4 du. So let's just substitute this. We have we have u equals something, and we have dx equals something. Okay, so wherever we see 4x plus 1, just replace it with u. Let's write our dx in terms of du. So we get dx is 1/4 du. And so now the integral of 4x plus 1 dx is the same as 1/4 the integral of u to the 1/2 du. And then, so this we know how to do, right? This we learned in, I don't know, was it section 5.2? To be honest, I can't quite remember. Okay, I think that something like that. Okay, so yeah, we just use the power rule. We add 1 to 1/2, and we divide by 3/2, or multiply by 2/3. And so yeah, the final, we just simplify this. 2 over 4/3 is 1/6. Make sure this is not your final answer, right? The original problem was written in terms of x, so make sure the final answer is written in terms of x. That's for indefinite integrals. Now, we're also going to do this with definite integrals, where the final answer is a number. So we're not so concerned with rewriting the answer. The answer will be a number, not some function in terms of x. Okay, so let's just look at a few more examples right here. Okay, so first of all, the one thing, this is a section on using the substitution, so all these integrals, just about all these integrals are set up so they can be done with substitution. I think what gets harder as we go on, we'll see an integral, and our first instinct is, oh, let's try substitution. Sometimes substitution doesn't work. So we learn all these techniques, and right now we have a limited amount of tools. We learn a lot more in Calc 2. So in Calc 2, we learn all these rules for evaluating integrals, and selecting which one applies. Can be kind of a skill. It's not obvious always which one to choose. But right now in this section, it's a section on substitution, so it's going to be substitution all over the place. So what's our inner function? We're taking sine of x squared, right? It's function composition. We're taking okay, so we're taking sine of u. So sine of u, where u is equal to x squared. So we have to change that dx to du. So du we'll use the chain rule, 2x dx. And now this is and now what do we have? We have x and we have x and we have du. Let me say, we have x and dx, and look what we have here. We have x dx. So let's just solve for x dx. So we want to make sure the whole thing is written in terms of u. In this case, it's kind of nice. We have x dx is equal to 1/2 du. So we have to recognize, yes, we have, if I just rewrite this, sine of x squared x dx, right? So you have to realize, so in this case, you have to be careful. The x dx du can be written as x dx. So just make sure there's no x's involved. Everything is in terms of u. And now what we have here, we just replace. And so x dx is 1/2 du. And so we also get sine of u. And so yeah, that 1/2 is not is under the. That 1/2 is 1/2 multiplied by sine of u. So we get this function here. Oh, we know the antiderivative of sine of u is minus cosine. So we get minus 1/2 cosine u plus c. And remember, our original substitution was u equals x squared. Go back to the original variable if it's indefinite integral. And so here's there's several more examples here. So here's kind of a fun one. D here. So here you might say, okay, well, I've got two trig functions, sine of x and cosine of x. And so, maybe you make a mistake at the beginning and you say, okay, let's let u equal sine of x. You're not going to be able to get rid of that square root of cosine of x. So, okay, in this case, we're taking its function composition, the square root of cosine of x. So we'll let u, in this case, be the inside function, which is cosine of x. But we're really lucky. See how du is the product of sine of x dx, isn't that what we have there? So we can get rid of that sine of x dx with du. And so what do we get here? We just get sine of x square root of cosine of x dx just becomes u to the 1/2 minus du. And just take the antiderivative, you get minus 2/3 u to the 3/2. And now just replace u with cosine of x and you get the correct answer. And so here's one more, and then there's kind of a nice section here. And some of these, see, substitution, here's an example. It's like substitution doesn't always work. When this is what we have to be careful is we like substitution, but it doesn't always work. Okay, so here we have square root of x squared times x. So when we know when you let u equals x squared plus 1, so when you evaluate du, you're going to get this product x dx. So there has to, see how we have this x dx here. Now the second case, it's just the square root of x squared plus 1. Now in Calc 2, you will learn something called a trig substitution to evaluate this integral b. So this integral b, this is not for Calc 1, it's for Calc 2. But it's a substitution won't work. And that's what I'm saying. You eventually you'll learn all these methods of substitution, and for some problems they don't work, and so we just say, oh, well, let's move on to the next one. Okay, so that's kind of what's hard about calculus or mathematics in general. You have so many techniques to solve these problems, but which is the right technique? Okay, so let's just look at this interesting section here. Which of these integrals can be involved using the substitution method? So, well, here, number one, we don't have x raised to like a power, right? So you can just let u equal 3x, and so du is dx. But here, if you let u equals x squared, you're going to get an x dx. Well, we don't have that in the original problem, whereas we do have an x dx in problem 3. So x times sine of x squared can be evaluated with substitution. And so here's another one, sine of x squared. Well, that's kind of not our friend, is it? Okay, so anyway, in this case, we can't do it with substitution. And and eventually, there's actually, I think in Calc 2, you learn how to integrate that sine of x squared. But here in 5, it was just simple substitution, right? The inside function, here we're evaluating like something squared. And what we're squaring is sine of x squared. So the inside function is sine of x. And we know that du is cosine of x dx. So in that case, you can use substitution. So for this section, the problems are set up so we can do substitution. Okay, now here comes the most important, important part. It's probably one of my favorite parts of the course, right here. So the end. So we're almost at the end. It's like the highlight of the course, right here. So okay, so let's do a definite integral with substitution. So square root of 3x plus 1. And we don't actually have to go back. We don't have to go back to the original variable in this case. The important thing is that we change our limits of substitution, which a lot of students don't do, and I get kind of frustrated with that. Okay, but I think the MyLab does a pretty good job of emphasizing this. Okay, so you let u equal there. So here's our inside function, 3x plus 1. The du turns out to be 1, so 1/3 du turns out to be dx. And so when you integrate, okay, so you get the integral of the square root of 3x plus 1 to the 1/2 turns out to be 1/3 u to the 1/2 du. Oh, but look at the limits of integration change. See, when x is 0, well, you plug x equal to 0, then you get u equals 1. And when x is 8, well, 3 times 8 plus 1 is 25. Right, so just make sure. So instead of the limits of integration being from 0 to 8, you get them from, it's from 1 to 25. And so now we can just evaluate this integral here, the square root of u times 1/3 from 1 to 25. You don't have to go back to the original variable. What I'm saying is what some students do is they'll go like this. What I've seen here is, okay, 1/3, the integral, here we go, 1/3, okay, from 1 to 25, and now we're going to, oh, I'm sorry, they keep the original limits of integration. That's what I'm complaining about. 8 to 0 square root of u to the 1/2 du. Okay, sorry, sometimes it's difficult to print. Okay, so you see, this is wrong. So this is wrong. Okay, so see, because see how it's a different variable, right? They're different, right? So now the first was 3x to the 1, 3x plus 1 raised to the 1/2. Okay, so it's not equal to the integral of, that'd be like that's equal to the integral of x to the 1/2 from 0 to 8, 10 multiplied by 1/3. So when you change the variable like we're doing right here, u equals 3x plus 1/2, you must change the constant, you must change the limits of integration. Now, another way to do, if you don't like this limit, this is the way I would do it. If you don't want to change the limit of integration, so here's another way to do it. You just, you do the indefinite integral. And so you get to the, so we do the, again, the substitution. The integral of 3x plus 1 to the 1/2 is 1/3 u to the 1/2. And so that's 2/9. So this integral right here, u to the 1/2, right? You just add 1 to 1/2, you get 3/2, and divide by 3/2 or multiply by 2/3. And so you get this indefinite integral 2/9 u to the 3/2 plus c. And what you can do is now go back. If you want to use it, now you can just go back to the original variable. So you replace that u, remember our u is 3x plus 1. So wherever you see u, you put 3x plus 1. And so now you can use the original limits of integration. And you better get the same answer, okay? So, that's really, students, this is really, you pretty much know everything. So here's another one. Yeah, so here, so a lot of times you see these square roots in the denominator. So again, just let u equal 2x plus 1. Oh, so now we'll get, actually, instead of the square root having some kind of function in it, it's just the 1 over the square root of u, which makes it a lot easier to integrate. And notice, once again, we change our limits of integration. Instead of being from 1 to 5, you let u equal 2x plus 1. So when x is 1, well, you get 1 again. Okay, so that's by luck. Okay, and when x is 5, 2 times 5 minus 1 is 9. So there's no need in these definite integrals to go back to the original variable, because the answer is just going to be a number. Okay, so let's do, maybe just do one more problem. This is one of our favorite problems in the course. So this looks like, whoa, look at this. So we get sine of x over 1 over cosine squared. Oh my God, how are we going to do that? Okay, but now we know about substitution. Okay, so we let u equal cosine of x, and yeah, so we get du. So luckily we have a sine of x dx in this problem, and so du is minus sine of x dx. So solve for sine of x dx, you get minus du, and so I think in this problem, this problem, I'm just looking at the notes. Yeah, so they're going back to the original limits of, yes, someone else wrote these notes for me. They're going back to the original limits of integration, but just look right here. We don't actually have to do that, right? You go right here. You go right here. So sine of x dx is minus du, right? And then 1 over u cubed. And again, so now when x is 0, u is 1, because cosine of 0 is 1, right? And when x is pi over 3, cosine of pi over 3 is 1/2. So the integral from 0 to pi over 3 of sine of x over cosine cubed of x is equal to minus the integral from 1 to 1/2 u to the negative 3. And you just evaluate. See, I think you can just, all you need to do is evaluate this. There's no need to go back to the x variable. So the integral of u to the negative 3, you add 1 to the exponent, you get u to the negative 2, divide by negative 2. And of course, then we still have that minus sign in front. And now we just use the fundamental theorem of calculus. And so it's negative, yes. And so we have a minus over negative 2. So it's just 1/2. The minuses cancel. So it's u to the 1/2 to the negative 2 minus 1 to the negative 2. So that's 1/4 minus 1. And yeah, oh, I'm sorry. You'll get, yeah, you'll get, I'm sorry, you get, it's to the negative 2. So let's go down here. So you get 1/2 2 squared minus, and then again, 1/1 squared is this 1 squared. And so you get 4 minus 3 all over 2. So you get 4 minus 1 over 2, or 3 over 2. So I think this is a good problem right here. Or you can also go back to the to the original. You can do an indefinite integral, and you'll get the antiderivative is 1/2 cosine to the negative 2, and then you can just use the original limits of integration. So yeah, just be careful here, students. That negative one, you have 1/2 to the negative 2. Just remember that 1/2 to the negative 2 is equal to 2 squared. Because you have that negative exponent. And then we can actually do a differential equation again. Where you're looking for basically you're looking for a constant of integration. Okay, so let's look at this y prime. Let's find the antiderivative of 3x squared plus 1. And in this case, we're told that y of 0 is 3. So we'll use substitution, and we'll get that the antiderivative is, just go through all the steps. U equals 3x minus 1, du is equal to 3 dx. And so you get 1/3 du is equal to dx. So you get the integral of 3x minus 1 to the 5th dx is the same as 1/3 u to the 5th du, and you get u to the 6 over 6 times 3. So you get 1, so you get u to the 6 over 1/18 plus c, and go back to the original variable. So you get the antiderivative the general antiderivative is 1/18 times 3x minus 1 to the 6 plus c, right? Because you take the derivative of c, you get 0. So there's actually a lot of there's basically infinitely many solutions to the differential equation y prime is equal to 3x minus 1 to the 5th, except we'll actually get a unique solution because there's only one where y of 0 is 3. Okay, so now let's say we want to solve for c. So to substitute x equals 0, so when x is 0, y is 3, so we get this equation right here, right? Our x is going to be 0, so we get 3 is equal to 1/18 times negative 1 to the 6 plus c. Well, negative 1 to the 6 is just a 1, right? And so we get 3 minus 1/18, so we get 53/18. So the solution to the differential equation is y equals 1/18 times 3x minus 1 to the 6 and plus 53/18, because yeah, we're specifying we have an initial condition. And so why don't we just stop there? There's more problems, but they're all pretty much the same idea. So substitution is really, again, definitely be on your test, and you'll see it all over the place in Calc 2, along with other techniques. So now I'm trying to stop the recording. I'm kind of like installing as I'm trying.